Hi everyone, today a video on Equilibria, looking at chemical equilibrium and the Chateliers principle. So some reactions are reversible. Instead of having 100% reactants or 100% products, we end up with a mixture of both. And eventually we get a mixture in which the proportions of all components of the reaction remain constant. So whatever proportion we have of reactants and products, it remains constant, it remains the same. And this is what we call an equilibrium mixture. So a way to show this is to think about water evaporating. Let's imagine that we have a puddle out in the open. The water will start to evaporate, and this will continue until all the water has gone. Now the water hasn't disappeared, of course, it's turned into water vapour, gaseous water. Now the same process we can consider this to be in a sort of an open container. With no lid on the top, it's not a closed system, the water will simply evaporate and the gaseous water vapour can escape. And so over time, it looks like our water has disappeared. But now consider the same process occurring inside a closed container. The water will begin to evaporate, as it did in the open container, and the volume of liquid will start to get smaller. And the number of molecules that are in the vapour phase, i.e. the number of molecules of water vapour, sometimes called the vapour pressure, will increase. But now, because these gaseous molecules, these water vapour molecules, can't escape, because it's a closed system, some of these gas phase molecules will now start to re-enter the liquid phase. They'll start to condense. And so we have these two kind of opposite processes, condensation and evaporation, happening at the same time. And the key thing is that they will eventually occur at the same rate. So the rate of condensation and the rate of evaporation will be equal and they will stay the same. And this is what we call dynamic equilibrium. We have our forwards and backwards reactions, i.e. our evaporation and condensation, happening at exactly the same time and at the same rate. Now, this equilibrium of the water vapour and the liquid water could have also been reached by filling the same container with water vapour and allowing it to condense. So it doesn't matter whether we started with liquid water and allowed it to evaporate, or started with water vapour and allowed it to condense. So another key takeaway message that is equilibrium can be approached from either direction. So there are four conditions that apply to all equilibria, all reversible reactions. The first is that equilibrium can only be reached in a closed system where our reactants and products can't escape. So we saw this with the water example on the previous slide. But when we had our open container, once the water evaporates, becomes water vapour, those gaseous water vapour molecules can just escape. And so over time it looks like our water has disappeared. But in the closed system, we still have the evaporation occurring. We still form our water vapour, but now the water vapour can't escape. It can't go anywhere. And so it has no choice essentially but to start condensing and turning back into liquid water, and hence we end up with a reversible or an equilibrium reaction. The second is that equilibrium can be approached from either direction, and the final equilibrium position, as long as the conditions stay the same, will always be the same. Again, we saw this on the previous slide with the water. So we said we could either start with a container full of liquid water, or we could start with a container full of water vapour, and we would end up with the same reversible reaction, the same equilibrium occurring. And the final equilibrium position will always be the same as long as our conditions are the same. So this proportion that we have of reactants and products, or the proportion of water, liquid water and water vapour, will be the same depending on if we have the same conditions. So it doesn't matter whether I start with the liquid water or whether I start with the water vapour. It doesn't matter which way I approach this equilibrium reaction from. The final proportions of reactants and products, the final equilibrium position, will be the same. The third is that equilibrium is a dynamic process. It's reached when the rates of the forward and backward processes, which are going on at the same time, are the same. So this was our definition of a dynamic equilibrium. We have our forwards and backwards reactions occurring at the same time, and the key point here is at the same rate. So overall, it looks like there's no sort of no overall change. With our water example, we have the liquid water evaporating. We have the water vapour condensing back into liquid water. Both of those processes are happening at the same time, and the key thing is that they are happening at the same rate. And the fourth is that equilibrium has been reached when the macroscopic properties of the system do not change with time. Now, macroscopic properties you can think of as sort of things that you can see and things that you can measure quite easily. So this is properties such as density, concentration, colour, pressure. They're also sometimes called intensive properties. What this means is that they do not depend on the amount of matter that we have. It doesn't matter whether we have 1 gram of something or 10 gram of something. Essentially, these values don't change with that. Now, a reversible reaction that can reach equilibrium, an equilibrium reaction, is denoted by the symbol shown on the right, this kind of double half arrow symbol, this reversible reaction arrow. And so I always think of it as a sort of full normal reaction arrow that's been split in half, and one of them is going one way, the other is going the other way. Now, PowerPoint doesn't have that symbol, and so I'm denoting the reversible reactions with this double-headed arrow. But if you're writing a reversible reaction down, you must use that proper equilibrium symbol that's shown on the right, the 2 half arrows going in opposite directions. Now, another key thing is that an equilibrium mixture can have proportions of reactants and products that can be any ratio. It doesn't have to be half and half. It doesn't have to be 50% products, 50% reactants. It could be 10% products, 90% reactants. It could be 90% products, 10% reactants. It doesn't matter what our proportions is, as long as it's not 100% reactants or 100% products, it's a reversible reaction, an equilibrium reaction. And so the proportions may change depending on the conditions of the reactions, and we'll see this come into play in a few slides' time. So, for example, if I change the temperature, if I change the pressure, if I change the concentration, the position of equilibrium, i.e. the proportions that we have of reactants and products, will change. But the really key takeaway is that at any given constant conditions, the proportions of reactants and products, the position of the equilibrium, does not change. Now, I always kind of think of this maybe as a kind of almost like a timeline going from 0 to 100. If 0 is all reactants, 100 is all products. Let's say we have a 60% products. You can imagine that the position of that equilibrium is on 60. So what we mean by position of equilibrium is simply the proportion of reactants and products. So this then brings us on to something called Le Chatelier's principle. And so as we've seen, it is possible to change the proportion of reactants and products in an equilibrium mixture. To do this, though, we have to change the conditions. And so this could be that we want to change the proportion of reactants and products because we want to obtain a greater yield of products. If we end up with a 50-50 mixture of reactants and products, it would be quite good to be able to get more product out of that to increase our yield. So it would be great to be able to change it to a 30-70 mixture or a 20-80 mixture. And so this is called changing the position of the equilibrium. So if we think of a kind of general reaction, A plus B goes to C and D. A and B are our reactants on the left-hand side. C and D are our products on the right-hand side. We say that if the proportion of products in the equilibrium mixture is increased, then our equilibrium has moved to the right. We've gone from reactants to more products, left to right. We also call this the forward direction. If the proportion of products in the equilibrium mixture has decreased, if we've gone to make more reactants, then we say the equilibrium has moved to the left or in the backwards direction. And again, the position is altered by varying conditions, such as temperature, pressure, or concentration. And so Le Chatelier's principle tells us that whether an equilibrium will move to the left or to the right when we change a certain condition. So Le Chatelier's principle states that a system, if it's at equilibrium and it's disturbed, the equilibrium will move in the direction that tends to reduce the disturbance. The idea being here really that the chemical system that we have doesn't want to be changed. And so if I produce a change in that system by changing a condition, the system moves to oppose that change. It will move in the opposite direction to reduce that disturbance, to get back to the point at which it was at. And so if a factor is changed that affects the equilibrium position, the position of equilibrium will shift to oppose that change. Now, an important little point here is that Chatellier's principle doesn't tell you anything quantitative. It doesn't tell you how far the equilibrium has moved. It can't tell you anything about the quantities involved. It simply tells us whether we can move towards the left or towards the right, i.e. to more reactants or to more products. So let's look at some examples of changing some conditions. The first one being if we were to change concentration. So if I increase the concentration of one of the reactants in my reaction, the Chateliers principle states that the equilibrium will shift in a direction that tends to reduce the concentration of this reactant, i.e. it will shift in the direction that uses up that excess reactant. Remember, the Chateliers principle tells us that the system will move to oppose whatever change we've introduced. So if we increase the concentration of a reactant, the Chateliers principle moves to reduce the concentration of that reactant, to use it up. So if I have a really simple reaction, A plus B goes to C plus D, if extra A was added, the only way the system can reduce the concentration of A is to react it with B, forming more C and D. If I add more A in, the only way I can get rid of it is to react it with the other reactant to make more products. So adding more A uses up more of B, and it produces more of C and D. And because we've produced more products, we say that the equilibrium has moved to the right or in the forward direction. So there's now a greater proportion of products. We could have also achieved the same, i.e. the equilibrium moving to the right, by adding more B. That would have reacted with more A and produced more C and D. Or we could have reduced the concentration of C and D. Now, a way to do that is to reduce C and D, by removing C and D, as soon as it forms in the reaction. If I reduce the concentration of C, essentially, the equilibrium moves to oppose that change, to increase the amount of C, and the way it would do that is to react more in A and B together. Another example is to look at changing the pressure. Now, pressure changes only affect reactions that involve gases. So changing the overall pressure will only affect the position of an equilibrium if there are different numbers of molecules on either side of the reaction. So pressure is only important for two cases, where we have a gaseous reaction, where everything is a gas, and if we have different numbers of molecules, different numbers of moles, on either side of the reaction. So an example here is to take N2O4, and this is in equilibrium with nitrogen dioxide, NO2. Now we can actually visually see this because N2O4 is a colourless gas, nitrogen dioxide, NO2, is a brown gas. Now if I increase the pressure of a gas, that means essentially I have more particles in a given volume. It's essentially the equivalent of increasing concentration in solution. That's certainly how I think about it often. If I'm increasing pressure, it's the same as increasing concentration in a solution reaction. I've got more molecules in a given space. So if I increase the pressure, i.e. I have more molecules in my reaction space, the Chateliers principle tells us that the equilibrium will move to oppose that change, and hence it will move to decrease the pressure. Now, decreasing the pressure would be the same as having fewer molecules in the same area of same volume of space. And so in this case, if we have our N2O4 to 2NO2 reaction, if I increase the pressure, the Chateliers principle will actually move to the left. And the reason it moves to the left is because there are fewer molecules, fewer moles of gas on the left-hand side than there is on the right-hand side. And so therefore less pressure is exerted. So by increasing the pressure, the Chateliers principle tells us that we want to move in the direction that opposes that change. That is to reduce the pressure, and in this case, we have to move to the side with the least number of molecules on. In this case, that's the left-hand side. And so we can actually see this if we look at the picture on the right. So this is the opposite now. We are decreasing the pressure. So we have our gas syringe containing our brown gas, our nitrogen dioxide, NO2. And we can decrease the pressure by pulling out the syringe barrel. Now for a moment the mixture would become a slightly paler brown colour because in doing that we've reduced the concentration of the brown NO2. We essentially have a fixed amount of NO2 molecules in that equilibrium mixture, in that volume. By moving the plunger out, we increase the volume, and so you can think of it as like adding more solution. Our concentration would decrease. But then the Chateliers principle comes into play. We want to shift the equilibrium to oppose that change. If we decrease the pressure, we have to oppose that change by increasing the pressure, and that is going to the side that has more molecules on, which is the brown NO2. So after a few moments, our mixture again would become darker because the equilibrium here is shifting to the right and producing more brown NO2. And so if the reaction has the same number of moles of gaseous species on either side, then pressure has no effect, because essentially we have the same number of molecules of reactants as we do products, and so changing the pressure does not affect the position of an equilibrium reaction if we have the same number of products as reactants. Now we can also think of the Chateliers principle for some other ones, such as changing temperature and for catalysts. But remember that in equilibrium, both the forward and backward reactions are occurring at the same time. And the key thing for the dynamic equilibrium is that they are happening at the same rate. So the concentration of the reactants and the products remains constant. If they're happening at the same rate, we can't be having more of one or the other. The concentration of the reactants and products, the proportions of them, remain constant. Now, increasing the pressure or decreasing the volume of a mixture of gases, like we saw on the previous slide, increases the concentration of all the reactants and products by the same amount, not just one of them. And so the rate at which equilibrium is reached will be increased by increasing pressure, because there will be more collisions in a given time. So this goes back to our thinking about kinetics, that simply if I increase the pressure of a reaction, I'm going to make that reaction happen more quickly, because now I have more molecules in a given bit of space and more molecules in a given volume, and so they're more likely to collide successfully to produce the products. A key thing as well to pull out from this is that increasing the pressure is the same as reducing the volume. The two are sort of inversely proportional to each other. So another way that you can think of it is increasing pressure is the same as reducing the volume, i.e. having the same amount of molecules now in a smaller space. Decreasing the pressure is the same as increasing the volume. So if we have a decrease in pressure, you can imagine it's the same thing as now having less molecules in the same amount of space, or the same amount of molecules in a bigger space. If we now look at changing temperature, let's suppose we have an exothermic reaction in the forward direction. And let's say that we increase the temperature. So here's our reaction, A plus B goes to C plus D, and our enthalpy change, delta H, is negative 180 kilojoules per mole, exothermic, releasing heat. And so the negative sign, remember, means that we give out heat, and that's in the forward direction. And so in the endothermic process, this will be the reverse direction. So A plus B going to C plus D is exothermic. The reverse, D plus C going to B plus A, is endothermic. Now, the Chateliers principle states that if we increase the temperature, the equilibrium will shift in the direction that cools the system down. Remember that the Chateliers principle wants to move in the direction that opposes the change. So if I increase the temperature, the system will move in the direction that can reduce the temperature, i.e. to take heat in, and that's the endothermic direction. This is the direction that is absorbing heat. So if I increase temperature, I'm producing more heat into the system. Therefore, the equilibrium is going to shift in the direction to essentially get rid of that excess heat, to absorb the heat. That's the endothermic direction. Endothermic means to take in heat. Remember, exothermic is to release heat. And the endothermic direction is the reverse direction, and so we say our equilibrium would shift to the left. If the equilibrium shifts to the left, then our equilibrium mixture will contain more of A and B. And likewise, on the opposite side, if we were to cool the mixture down, then our equilibrium would shift in the to oppose the change. To oppose this cooling of the mixture, we'd want to release heat, and so it would move in the exothermic direction, or to the right. And then finally, to look at catalysts. Now, catalysts have no effect on the position of the equilibrium. They do not alter the composition of an equilibrium mixture. So if I have a particular reaction, A plus B goes to C plus D, there's a particular equilibrium position in the conditions that I've stated. If I now do this reaction in the presence of a catalyst, I have exactly the same equilibrium position. I have exactly the same proportions of reactants and products. They do not alter the composition of our equilibrium. Remember that a catalyst works by producing an alternative pathway for the reaction, one that has a lower activation energy. And a lower activation energy means that we have a faster rate of reaction. Catalysts speed up chemical reactions. So what this means is that it affects the forward reaction, but of course we know that equilibrium reactions are reversible reactions. So it doesn't only affect the forward reaction, it also affects the backward reaction. And it affects the forward and backward rates equally. And because it affects both the forward and backward rates equally, essentially the effect of the catalyst cancels out. It's like having +1 and -1 equaling 0. The effect of it increasing both the forward and backward rates equally means that there's actually no change in the composition of the equilibrium mixture. So catalysts don't affect the yield of a reaction, the proportions of product that we get out, but they do allow equilibrium to be reached faster, and therefore they're very important in industry. So even though we might not be able to get more product out by using a catalyst, it could mean that we have our equilibrium reaction being set up in 1 hour rather than 2 hours. And so they are important in industry. So they affect the rate of equilibrium attainment, they don't affect the position of equilibrium or the composition of our equilibrium mixture. So many industrial processes involve reversible reactions, but obviously yield is important, right? If we think about an economic standpoint, we have to buy our reactants. We want to produce the maximum amount of product we can in order to sell that. Now, the Chateliers Principle can be used to help find the best conditions for making sure we get the best yield. However, there are other important considerations too. If you've got an industrial plant, there's obviously going to be energy costs, costs for running the plant, and so there are other conditions to think about. If we have an equilibrium reaction where we've considered the Chateliers Principle, and the best conditions that we get out of this is that we have to run it at a really high temperature and a really high pressure, well, that could give us a fantastic yield, but it might be that actually it's not economically viable. The cost of running the plant at such high temperatures, such high pressures, the energy cost of doing that would outweigh the more product that we would get out of that equilibrium reaction. It could be that we have our best conditions being a very low temperature and low pressure. The problem with this, though, while there isn't necessarily so much of maybe an energy cost with using a lower temperature than a higher temperature, at lower temperatures and at lower pressures, this is going to slow down the rate of a reaction. So we might be able to get a fantastic yield out of it, but the reaction might end up taking 7 days to complete. And so often, a set of compromise conditions are used. So, for example, we can look at the Haber-Bosch process for making ammonia. We have nitrogen reacting with hydrogen to produce ammonia, and this is an exothermic reaction. Our delta H has a negative sign. So if we think about the Chateliers Principle, if we have high pressure, remember that when we have a gaseous reaction, we can consider pressure. We don't have an equal number of molecules on either side. We have 4 molecules on the left-hand side, 2 molecules on the right, so pressure will affect this reaction. If I increase the pressure, a high pressure, the equilibrium is going to shift in the direction to oppose that change. It's going to shift in the direction to reduce the pressure. That's to go in the direction that has the least number of molecules on, and that's the product side. So a high pressure would increase the yield of our products. Likewise, if I had a low temperature, well, a low temperature is the same as kind of taking in heat, essentially. And so if we lower the temperature of our reaction, equilibrium is going to want to shift in the direction that increases the temperature through the Chateliers Principle. And the direction that's going to increase the temperature is the exothermic direction, the one that gives out heat. And so that's the forward direction, again producing more product, more ammonia. So our best conditions for this would be a high pressure and a low temperature. But actually most plants run at a slightly lower pressure and a higher temperature than would give the maximum conversion. And this is a set of compromise conditions. Now the gases, the nitrogen and hydrogen, continuously flow over the catalyst. And so what it means is that they don't necessarily spend long enough in contact with the catalyst, which is finely divided iron in this case, to really reach equilibrium. And so we say that there's a 15% conversion, roughly 15% conversion to ammonia. But rather than just discarding what we don't end up reacting, the unreacted gases are fed straight back into the reactor. Now we can also consider the atom economy of this reaction. And the atom economy for this is 100%. We only have one product, so all of the atoms from our reactants must go into making the product. And also, while the atom economy appears to be 100%, it's actually much less because the equilibrium is not actually reached when the gases flow too quickly. And so when we design the plant for this reaction, we have to devise the best compromise conditions between the rate of reaction. We want a quick enough rate of reaction, but if we have them flowing over the catalyst so quickly that they can't fully obtain equilibrium. So we have to have this compromise between the two. Another example is the production of methanol. So this is carbon monoxide plus hydrogen to produce methanol. Again, another completely gaseous reaction. An enthalpy change of negative 91 kilojoules per mole. So again, another exothermic reaction. And the catalyst here is a copper catalyst. Now you may have heard of something called synthesis gas or syngas. This is what the reactants are, carbon monoxide and hydrogen. And this is produced by reacting methane with water, and we end up producing carbon monoxide and hydrogen. So currently the way to make methanol is we take methane, react it with water. This produces our synthesis gas. And the synthesis gas, the carbon monoxide and hydrogen, they react together to produce methanol. So the Chateliers Principle tells us that for maximum conversion, again, like we had with our Haber-Bosch process, we need high pressures and low temperatures. Again, compromise conditions are used, so we have a slightly higher temperature and a slightly lower pressure. And again, this produces actually a pretty small yield, 5 to 10% yield. But again, the gases that don't react again can be fed straight back over the catalyst. So, time to have a go at some questions. So we have lots of questions here to do with changing conditions of equilibrium. So if you want to have a go, pause the video and the answers will be on the next slide. So the answers, I'm going to start with the questions that were on the left-hand side in the red box. So we had to, for each of the following statements, say whether it was true or false. So the first was that once equilibrium is reached, the concentrations of the reactants and products do not change. That's true. Once we reach our equilibrium reaction, those proportions do not change. We have an equilibrium position that is constant. B is that at equilibrium, the forward and backward reactions come to a halt. Well, that's false. The reactions don't stop. It's just that the rates of the forward and backward reaction are happening at exactly the same rate at the same time. C is that equilibrium is only reached in a closed system. That's true. Think back to that water example right at the start. We had to have a closed system where our water vapour couldn't escape and had no choice but to start going in the reverse direction and condensing. And then finally D, an equilibrium mixture always contains half reactants and half products. That's false. It can be any proportion of reactants and products as long as it's not 100% reactants or 100% products. And then question 2 from this was what can be said about the rates of the forward and backward reactions when equilibrium is reached. The forward and backward reactions are equal. They are the same rate. Then moving on to the questions in the green boxes. So the first one here is this synthesis of methanol from carbon monoxide and hydrogen. And by reference to rates and concentrations, explain the meaning of the term dynamic equilibrium. So a dynamic equilibrium is where we have the concentrations of reactants and products not changing, and our rates of the forward and backward reactions are equal. So dynamic equilibrium, definition of it is 2 parts. The first being the forward and backward reaction rates are the same, and the second being that the concentrations, i.e. the proportions of reactants and products, don't change. Then explain why a high yield of methanol is favoured by high pressure. Well, remember that for all the species here are gaseous, so we can consider a change in pressure affecting this. We have different numbers of moles on either sides, different numbers of molecules, and therefore a change of pressure will affect this equilibrium. High pressure will shift the equilibrium to the side with fewer molecules, i.e. the lower pressure side. Remember the Chateliers Principle. We want to shift our equilibrium in the direction that moves to oppose the change. And so if we're increasing the pressure, the equilibrium will shift to the direction that has the lower pressure. The lower pressure, remember, is having less molecules in a given space, is a smaller pressure. And so it shifts to the side with the least molecules on, which is the right-hand side. We've only got 1 mole of methanol. And so because we're shifting our equilibrium in the forward direction to the right, we end up producing more methanol. Then it was suggesting 2 reasons why the operation of this process at a much higher pressure would be very expensive. If we're operating at a much higher pressure, well, then there's a much higher energy cost. So therefore that's economically less good. And the second is that if we operate at higher pressures, typically they're has to be more building regulations going on. We have to make sure that our plant could withstand the high pressures safely. And so we have to therefore potentially build out of more expensive materials that are stronger. And then the final question here was to state the effect of an increase in temperature on the equilibrium yielded methanol. We were given here that the forward reaction was exothermic. It released heat, had a negative enthalpy change. And so if I increase the temperature, the equilibrium will want to shift in a direction that opposes that change. That's our application of the Chatelier's law. So to oppose the change of an increase in temperature, it wants to shift in the direction that will reduce the temperature, will take in some heat. That is the endothermic direction, and that is the reverse direction, that is going back towards the reactants, the left-hand side. And so that will reduce the amount of methanol, reduce the yield of methanol. And then finally, it says that if a catalyst were not used in this process, the operating temperature would have to be greater than 700 Kelvin. Suggest why an increased temperature would be required. Key thing, remember that a catalyst increases the rate of our reactions. It provides an alternative pathway, one with a lower activation energy. It increases the rate of our reaction. And we know that one way to increase the rate of a reaction is to heat the reaction up. You give the molecules more energy, the collisions are more likely. So if we didn't have a catalyst, we'd have to increase the temperature. And then the other set of questions in the green box, we have this formation of nitrogen monoxide from nitrogen and oxygen. In terms of electrons, give the meaning of the term oxidation. So if you're not happy with redox oxidation and reduction reactions, go and look at my videos on the redox chemistry. But the key thing we need to remember here is the mnemonic oil ring. Oxidation is loss of electrons, reduction is gain. And so we say that oxidation is a loss of electrons. We then have to state and explain the effect of an increase in pressure and the effect of an increase in temperature on the yield of nitrogen monoxide. So starting with the pressure, everything in this reaction is gaseous, and so we can consider pressure. However, if we look at the number of molecules on either side, there's 2 molecules on the left-hand side and 2 molecules on the right-hand side. And so because we have equal numbers of molecules on either side, there's no effect of a change in pressure on this reaction. Remember that pressure changes are kind of driven by how many molecules are in a given space. If there's the same number of molecules for the reactants and products, well then a change in pressure is going to give us no change in the position of the equilibrium. An increase in temperature, well now we need to look at our enthalpy change. Our enthalpy change here is endothermic, positive enthalpy change, and so that's going to be taking heat in. If we increase the temperature, the application of Le Chatelier's law tells us that the equilibrium will want to move to oppose that change. It will want to move to reduce the temperature, to take in heat. That's the endothermic direction, which is the forward direction, and so therefore we increase our nitrogen monoxide yield. So thank you for watching this video. You can find more videos like this on my YouTube channel. If you found this video helpful, please consider leaving a review on a tuition website. I also offer tuition for chemistry, so you can check out those tuition websites for information. And if you need any more help with your chemistry, you can feel free to drop me an email. I'll be happy to help.